Okay, good morning, everyone, or good afternoon, if you're in the East Coast, and thank you everyone for joining. Our attendance is little light, but this program is being recorded, so people can listen in and enjoy the show. Today, actually, we have gathered for our recurring technical webinar. We have got several brilliant engineers from AABEA and from other places, and we're really grateful to all our panelists and the speakers and the attendees. So basically the topic of today's webinar is economic growth via semiconductor technology, and we're going to focus on design, service, manufacturing, inspection, and testing. So, and we have got four brilliant speakers. So let me introduce our first speaker, Mr. Enayetur Rahman. And then as we go to the subsequent speakers, I'm just going to talk about them a little bit, and then they will come forward and give their talk. So to tell a little bit about Mr. Enayetur Rahman, he's the founder and CEO of Ulkasemi Private Limited. He has guided the company to a leadership position. Raman has more than 35 years of experience in the semiconductor industry in engineering management, strategy making, resource building, product planning, and risk management. He started his career as a design engineer at AMD and held senior technical and management positions with OKI Semiconductor, Virtual Silicon, and Sintera Communication during his 12+ years of tenure at AMD. He was a pioneer in designing several interface logic chips. He has patents on data communication systems. Mr. Rahman received his Bachelor of Science degree in Electrical and Electronic Engineering from BUET, which is Bangladesh University of Engineering and Technology, Masters in Electrical and Computer Engineering from Oregon State University in Oregon. And he also attended engineering management courses in Stanford University, a very renowned school at the West Coast. So without further ado, let's welcome Mr. Enayetur Rahman. Let's hear.
Thank you, Faysal, and thank you, Anisbhai, and everybody for giving us the opportunity to present our company. So let me share my screen. Can everybody see my screen?
Yes. Yeah. Mm-hmm.
You can see it, right?
Yes, we can.
Okay. Yep. So today's my topic is, Ulkasemi history and journey. But before we tell Ulkasemi history, I think it's better to talk about Silicon Valley history, then Silicon Valley Bangladeshi diaspora history, and the connection with Bangladesh. Where do we stand compared to other countries in Asia? So what I would do is I will start a few minutes video about Silicon Valley, and then after that I will talk about Bangladeshi presence in Silicon Valley. So please watch this video.
And I'll pick the volume to Ramen.
Okay. Can you hear it now?
It's a little light.
Sorry about that. So I'm sorry about the whole thing because the volume was not clear.
It is very low.
It's एकदम maximize कर दें. हाँ, exactly.
Hello. What happened?
এটা ফোন করেনি না কামরুলরা আমরা যেতে পারবো।
Thank you very much. Sorry about the sound and everything. I think let's move on to, can you hear me clearly?
Yeah.
Okay,
Yes,
so
we can.
the actual thing was not, okay, let me.
It was a nice video, and but
Yeah, thank you. So no problem. I'll share this thing with you guys later on also. Okay. So let me tell you what happened today. The semiconductor industry, definitely Silicon Valley, everything started in 60s, 70s, 80s, and 90s. 4 countries in Asia took advantage of that. And 4 these big players was Japan, China, Taiwan, and South Korea. And later on, you see all those red marked other significant countries like India, Thailand, Malaysia, Singapore, Vietnam. So what is happening here is all those countries actually lobbied quite well to Silicon Valley, but Bangladesh never participated in all those things. So India, there was manufacturing mostly was done in other places, but India mostly took advantage of IC design service and everything. All those things started in late 80s and 90s. So what happened to the Bangladeshis in Silicon Valley? So Bangladeshi started coming in early 80s. I was one of the early comer. Mizan Bhai was there also. So there was a lot of discussion and initiative was taken because we saw all those Asian countries were taking advantage of Silicon Valley. We saw India was growing. There was absolutely nothing when we started in Silicon Valley in India. But then we saw Bangalore, we saw all those things are happening, but there was zero activity in Bangladesh. So, the AABEA Silicon Valley chapter opened in 2000, and actually I was the first president of Silicon Valley chapter. What we did is we decided to quickly do a SB 2000 conference. It was arranged in Silicon Valley. It was a resounding success in terms of conference. I think Bangladesh IT Minister General, I try to remember his name, and then also our what is that, trade minister and other minister came, couple of ministers came. And then Bangladesh government later on opened an office in Silicon Valley, 2003. I was the director of that office, but that office was closed in 2005. So there are certain things to discuss in future, what happened, why all those things did not succeed. And I think it requires a lot of discussion and debate and stuff like that so that we can do a lot better in future. But as far as private company is concerned, the first chip design company opened in Bangladesh, Power IC, started by a gentleman called Didarul Islam in 2005. And then 2006, the Silicon Valley company Fast Track opened their office in Dhaka, and both shut down very quickly. Without any good example, Ulkasemi started in 2007. in Dhaka. So what are the challenges in Bangladesh? I think the biggest challenge is lack of knowledge of semiconductor industry. Nobody has any idea, any clue what is semiconductor, how semiconductor industry works and stuff like that. Lack of awareness of Bangladesh by multinational companies also, because this is a two-way street. We have to tell them, we have to promote our country. That was not done. Then lack of understanding of immense potential of Bangladesh, in semiconductor industry. And then nowadays, when the industry goes, they say that there is absence of legacy. And then there is the absence of long-term planning and investment from the government in semiconductor side, okay? So what are the opportunities in Bangladesh? Bangladesh is a very homogeneous country, like Vietnam. A lot of things to learn from a country called Vietnam. Bangladesh has a huge available of engineering talents. This is a big thing, big plus. Bangladesh people can be easily trained and leapfrogging technology, even though we are behind in technology. I think the another advantage of Bangladesh is we can do resource augmentation with senior engineers from other locations to complete the project. We don't have to rely on junior engineers in Bangladesh. And Bangladesh government is always willing to help. And Bangladesh could be easily part of semiconductor ecosystem if all the measurement is taken properly. Now let me talk about a little bit Ulkasemi history. Again, we started our journey in 2007 with only 4 engineers in Baridihar DOHS, small 700 square foot apartment. As I said, there are 2 companies already failed. There is nothing to follow, and with some uncertain future. Okay. Our first engagement was with Viraj Logic in IC layout design. But unfortunately, even though our first project was very successful, the recession started, if anybody remembers, 2007, 2008 year. Then 2009, 2010 was a very slow time for us. Actually, there are a lot of doubts on many people's mind from Bangladesh side and from the Silicon Valley side, whether our company will succeed. So we engaged with a company called Micrel. We did some layout in PDK. Then we engaged with some Chinese company called Khorasan in Shenzhen. We did some work for them just to survive within that time, because it was not an easy time, if you remember 2008 to 2010. 2011-12, things changed a little bit. We engaged with one of the largest processor company for layout design work. And also we opened our PNR. PNR stands for Place and Route team. This is called Physical Design Team. In 2013, we received EEF fund from the government. We got exactly 2 koti 40 lakh taka. In fact, we were very happy to return the money 2 years before it was due, just to let you know. We successfully tape out PNR project with AM Logic. We engaged with Linear Dimension for IC layout. And we engaged with another company called KiloPass for memory layout and open front-end verification team. Just to let you know that 2011 onward, we are always profitable, okay? And another thing is that all those projects we are showing in between 2013 and 14, some of the project was very, very challenging. And pretty much I sometimes call them, it's guaranteed to fail, but we had to overcome with certain technique we applied. In 2015-16, we engaged with a big US semiconductor company called Maxim. We taped out almost 300 chips for them. We partnership with Designer's Guide for AM verification. There is an engagement with Invensys. There's another famous company in Silicon Valley. We engage with Texas Instrument. We engage with web computing. And this is one of the largest machine learning chip we have done in Bangladesh. 2017-18, we engaged with Qualcomm, and Qualcomm is one of the analog verification modeling. We created their library and everything. So I think our biggest success story came from Global Foundry. Global Foundry, one of the 4 largest fab foundry service in the world. As you know, TSMC, Samsung, Intel, and Global Foundry. So we are a big partner with Global Foundry. And we are doing mostly DTCO, it's called Design, Technology, and Co-optimization Service. We do all sorts of service. We have a huge number of engineers engaged with Global Foundry. Then we engage with Analog Bits, and this is also another one of the big IP company. We successfully tape out web computing machine learning processor. This was one of the most challenging and difficult job we had to do it in Bangladesh at 16 nanometer technology. I think more success story came in 2019-2020. Apple selected Ulkasemi as a vendor for IC layout service, which is a big deal actually. We engaged with Facebook and Google. We did some AR/VR chips for Facebook and Google. We are continuously working with them. We engaged with SigmaSense, digital verification service. We started processing for development, first made in Bangladesh chip, which we proposed to Bangladesh government. And also we opened, during the COVID time, you'll be surprised, office in Rajshahi, Canada, and India, Bangalore. And also during this COVID time, we got ISO 9000 certification. So this is 2021. I think the biggest achievement for 2021 is TSMC. As you know, TSMC is one of the largest foundry in the world. Actually, compared to second one will be Samsung. TSMC almost controls 70-80% of the world market right now. And with the advanced technology and everything, TSMC so far selected only 20 companies to become their DCA. DCA is called Design Center Alliance. We will be the 21st company, and they already approved us. We are almost finishing. Thanks to Mizan Bhai and my team did an outstanding job. As we speak, we are trying to finish all the remaining work, and inshallah we'll be starting in August with TSMC. I think if I summarize today, we have 200 plus engineers in 5 different locations. In Bangladesh, we have Dhaka and Rajshahi. We have Silicon Valley. We have almost 30 engineers in USA. We have a Bangalore team, and we have a Toronto team. Our goal is to do resource, augmentation. Any project comes in, we should be able to coordinate and execute any project. Again, I think as we move on, 2022, 23 beyond, inshallah, I'll be able to give you more success story of Ulkasemi. I think this is a story I want everybody to know that despite a lot of negative thing in Bangladesh, it is possible. It will be difficult. It will be challenging, but it can be done. Again, let me take this opportunity to thank again for the organizer to give us the opportunity. Thank you very much.
Thank you so much, Anwar. It's very impressive. So let's hold our questions until all the speakers are done talking, so that way we can go back and have a formal Q&A session. But thank you again, very impressive success in your company, Anwar. So let's move on to our next speaker, Dr. Mizan Rahman. Let me quickly brief you about his bio a little bit. So Dr. Mizan Rahman has 30 years of design and management experience from the Silicon Valley, specialized in chip design to full system design. Dr. Mizan Rahman brings product development and engineering management leadership to Ulkasemi. Mizan has extensive hands-on expertise on ASIC, SoC, PCB, and system design. Worked with Fortune 100 global companies like HP, Sun, and Cisco. He was awarded 14 patents. He was the co-founder of 2 successful startups, RMI, which is acquired by NetLogic, and Sysilk. Dr. Rahman is an active Stanford University alumni with a strong passion to help the poorest of the poor. He's the chairman and CEO of philanthropic organization RIJAK, RIJAKK.org. And Dr. Mizan Rahman has Bachelor of Science in Electrical Engineering, MS in Electrical Engineering, and PhD in the same, and also Masters in Computer Science. So let's welcome Dr. Mizan Rahman.
Well, thank you. This is Mizan Rahman. Good morning to everybody. Let me go share my screen.
Sure.
Can you see my screen?
Yes, we can.
Okay. Thank you. Thank you, Anis Bhai, Faysal Bhai, for giving us the opportunity to talk. My talk will be following as an extension of what Anwar described. What the silicon business looks like and what it means to Bangladesh. I keep saying for the last 35 years, I made all rich people richer. Got tired of that. So we start focusing on Bangladesh instead for last at least a decade. So this, we all know the presentation is made more of a general Bangladesh-oriented, semi-technical or technical people. So bear with me. Most of you know all of these, but the question remains: everything in the heart of everything is the chip. Whatever you do during the day, starting your coffee machine, driving your car, or even going to sleep, your Apple phone is ticking away. Everything has an IC in it. So there cannot be a better market than this. So, and here is an opportunity, and the world has taken the opportunity, and it is our opportunity to lose.
Yeah, but can you do it in display mode? Yeah.
I thought I did. Okay. Is it better? Yes. So can you hear me?
Yes.
Okay. So IC is good, but the job creation of IC will be less than the system. So I'm just trying to display where IC is the foundation, and then comes the system, then comes the software. Of course, job creation will be different in different sectors, but we should not focus on only IC, where most of the revenue, business, and job creation is in the upper side of the IC. But we cannot jump in the system without expertise in the IC. So just very simple: chip goes to a board goes to a chassis with a line card, and then we load software or apps, we have a solution. And world looks for a solution, and we should be coming forward with the end-to-end package of a solution. And there are hundreds of engineers with that quality available to help Bangladesh. They are Bangladeshi. We need to make them aware that we are done 25 years or 30 years of work doesn't mean that your life ended. Let's move on to retirement home and relax. That should be a disservice to the country. And we studied all free. It is time for us to get back to the country. And by the way, we take all kinds of expertise, the consultation, discussion, reviewer, or opening a door for any Bangladeshi company. You should, or all should, come forward. Now, very simple, whole semiconductor process, you guys all know about it. There is an architecture, implementation, verification, netlist generation, physical design. We do all of these in Ulkasemi today. So that a perspective, sitting in Dhaka, we do all of that. Now, then comes the fabrication. It's a big ticket item. There is a lot of discussion about it. I have my own personal opinion. I don't want to discuss. I want to pause right there. But what we need to focus on is the wafer sort. And is why that's what I was talking to you about it. This is about to happen. It's a matter of some lining up some arrows, and we will have it. Wafer sort, wafer packaging, testing, we are good at, we know how to do it. It's the matter of ecosystem is not there yet. Doesn't mean that opportunity is not there. And Ulkasemi is pursuing that, and as we speak, both in Bangladesh as well globally, where and how we can penetrate. Remember that these are big ticket items, a lot of money needed. That's where we don't want to jump in. We run a very tight ship. Well, objective is not to just expand, get the job, and go on and take a big $10 million loan from a bank and then see what happens. We don't run the company that way. We are we are staying profitable and invest all the money we can. We don't want to borrow any money, then we cannot pay. So production, of course, you cannot go to production if you don't have your own IC. So we are struggling at this point. Very healthy, very good opportunity in Dhaka. So if you look at the global market, semiconductor today is half a trillion dollar business, hands down, $500 billion business. We have all the expertise, can do it. We can all say that, oh, China took all the market. You guys not gonna be able to compete with them. I don't buy that. Good thing is, whole market is taken over by Asia. If you look at $1 trillion space, out of 300 to 400 billion, 350 billion is in Asia. So, it is time. World has just flipped. It is not USA anymore. We are all US citizens. So I love both countries, and wherever as a businessman, opportunities in Asia rather than in America for now. Now, Asia is not in this story, is not that. The real story is the fab space. If you look at the fab of the world, you can see how big the TSMC is. It is mind-boggling how big the TSMC is and how powerful is TSMC is. If you combine just the China, Taiwan, and South Korea, it counts for 90% of the semiconductor chip manufacturing. And that can trigger a World War III. As simple as that. You have seen a lot of tension in our previous president, and it is not gonna go away. It is a real security issue. And once the chip is made, you do not know what's inside. What it takes to change the country. I just want to take a minute to show you Dr. Maurice Cheng from China, studied in MIT, PhD at Stanford, worked for TI. He was pushed out of TI because he was an Asian man going to a vice president. If you know him, talk to him, you'll know how humble, how knowledgeable that guy is. The politician of Taiwan says, well, we are an agricultural country, let's make it an IT country. Just like we are discussing today. Back in '85, they got together and said, let's do some fabrication, IC, whatever. Then he figured it out, maybe it's a good time to do a fab. So he founded TSMC in '87. Today, it is a $50 to $60 billion company. That's not all. What is the key point is, his engineer started the transformation of China. Is about 15 years ago. So a single individual with the support of the country can reshape Asia. Today's success of Asia, if I want to give it to one person, I will give it to Maurice Cheng. Taiwan is not the only story. Samsung is. Samsung is another player coming in last 30 years. Think about that. Number is 1.23 trillion. I'm not saying billion. They make their own 1.23 trillion chips. If you put a dime or a penny in it, we're gonna make it. So think about that. 30 years ago, nobody knew who Samsung is. Here they are. Now, India. When I did my first startup, I was in a VC meeting to raise my money, and they stopped my meeting and had a conversation that let's do investment in India. Everybody in the room laughed at it. In 2000, exactly in 2000, they laughed at it. Say, India chip design? You gotta be kidding me. Cows are walking in Delhi and Bangalore, and you gotta be kidding me. But look, In 2020, it's a $33 billion company. There are 3,000 chips are designed every year. 30,000 engineers work on chip design and verification. And there is no way we can be zero in this case. And I suggest that tells you where the opportunity is. So IoT, 5G, AR, VR, AI, ML, you name it, all is the disruption. This is the point we should jump in. If you are waiting, wait no more. So these are in billions. In a 2030, which is less than 9 years away, it will be in $1 trillion space. And I can go on and on, doesn't matter. The fact is, this is the right time. There will be billion smartphones going to be sold. And once the 5G is here, everything will change. Every device will be redesigned. How to monetize that, hardware is a critical piece as good as software, even though they dominate. So here we are. My interest in a hardware side and system side, so I gear towards that, but the market is in every sectors. So again, we are all worried about Bangladesh, point A to B in Dhaka city takes 2 hours to go. Well, at least you can go there in 2 hours. This Silicon Valley, you have to run your horse cart to take 2 hours, or at least 2 hours to go from Palo Alto to this. This is where I live nearby this place. This is in Cupertino and Sunnyvale. And 50 years ago, it looks like this. And then now it looks like this. Exactly same location, same road, same building. Apple is there. Before Apple, you do not see the transformation. This is where the Apple's HP computer company was. And that's what I work with them. They demolition and build the HP, and that got removed and Apple came in. So if anybody is talking Bangladesh, no, nothing happens, think again. These are inevitable. We don't need any government. We don't need any politician to help us. Don't stop our growth. Let us, even today, if I DHL a package from here, China to Dhaka, it gets stuck in the airport for two weeks. I didn't say 2 hours, 2 weeks. So those are finite things we have to solve. What we are after. Bangladesh is, made in Bangladesh now has a value. 15 years ago, if you say made in Bangladesh, people will run away. I'm gonna wear a shirt from Bangladesh, but now there is a value. Believe me, people trust Bangladesh right now. And it is the second largest volume producer. That is the only exporting. If you look at the IT, worldwide is $500 billion service market. Outsourcing, I'm only talking about outsourcing. India is 140, we don't even exist. 0.7 billion is a made up number, I would say. So we don't even show up. Most of the number in here is the freelancers, software, because the infrastructure is not there. So we are committed. We will focus on it to change it. And we are not waiting for anybody. We are not looking for anybody's help. We should do our own, and all the support we can get, we will. We are not shooting in the dark. We did startup, successful startup. I delivered it. I took money from the VCs, and I will never take money from VCs anymore. I'm done with them. At this moment, I'm working on 2 startups. One is Ulkasemi, another one is Teton, which is funded by Ulkasemi, and that is mostly focused on the system side. If I've given an opportunity in the future, we'll talk about Teton. So what is preventing us? Bangladesh is totally focused on the software ecosystem because it is easy to do. A bunch of some money, engineer, PC, you're done. The rest of it, we know what to do. So just apples to apples, hardware doesn't work that way. As the NRE cost, there is a tools just cost $1 million. If you go on a lower node, tool may cost, $10 million. Tape out is tens of millions of dollars. Where that money gonna come? And you don't see you don't see the price of the chip or the income from the chip until 3 years. You can say all of that, but nothing gonna happen. So my rule of thumb is a full-time expensive. Well, Apple relies on Ulkasemi and Bangladeshi team. As I said, Bangladeshi team, your Apple phone chip is designed by Bangladeshi engineer. And we are doing a tape out of 3 nanometer, which is not in the scale. If you go to the TSMC, they are not going to talk about 3 nanometer, 2 nanometer. We are working on 3 and 2 for multiple companies. That's all I have today. And thank you for listening.
Thank you so much, Dr. Rahman, Mizan Bhai. It's really impressive. And it's an amazing growth that we can see, the impact that you're making in Bangladesh. It's really, really impressive, very impressive. So let's hold our question until at the end. So let's move on to our next speaker. Our next panelist is Dr. Mehdi Anwar. Let me talk a little bit about Dr. Anwar. He currently serves as a tenured full professor in the Electrical and Computer Engineering Department at the University of Connecticut, as a National Academy of Science, Engineering, Medicine, Jefferson Science Fellow. He served as a special advisor for technology transfer and innovation in the Office of Intellectual Property Enforcement, Economic Bureau, U.S. Department of State. Dr. Anwar has assisted the United Nations Office of the High Representative for the Least Developed Countries, Landlocked Developing Countries, and Small Island Developing States to stand up the newly established United Nations Technology Bank for the Least Developed Countries. Dr. Anwar has served as the Associate Dean for Research and Graduate Education, School of Engineering, from 2006 to 2009, founding director of the Department of Homeland Security Center of Excellence, interim director of the Connecticut Global Fields Call Center, and interim department head of ECE from 1999 to 2001. He was an IPA at the Sensors Directorate, Hanscom Air Force Base, working on advanced metamorphic HEMTs and GaN-based hefts, pioneering the design of low-noise antimony-based compound semiconductor HEMTs. He has presented over 40 plenary and invited talks at the National International Conference, published over 240 research articles and book chapters, and edited 9 volumes. Dr. Anwar served as the founding editor of IEEE JEDS and served as the editor of the IEEE Transactions on Electron Devices between 2001 and 2010. He was a guest editor of Optical Engineering, conference chair of Terahertz Physics, Devices and Systems at SPIE DSS and Sensing between 2009 and 2016. And Dr. Anwar is a SPIE fellow. So let's welcome Dr. Anwar, and let's get started with your speech, sir. Thank you.
Dear Faysal, that was a rather expanded introduction.
No, you deserve it.
I don't think so. But it is actually an honor to share this platform with Enayetur and Dr. Mizan Rahman. Raman, I've not met him yet. And definitely, Anis Bhai, thank you so much. And I see our Saifur Rahman sir is also there. So let me share. So what I will do is, so we are going to, simply switch gear a little bit and move towards a little bit of engineering. And I then think Dr. Rahman, Anwar Rahman Bhai will actually delve more into the science aspects of semiconductors and so on. So let me follow the cue that was Dr. Rahman made a presentation. And out of that huge, $500 billion market, a sizable amount or a sizable number of electronics happens to be counterfeits. And that actually raises a red flag, because there are certain implications, and most of it actually is security related. That's something we'll actually discuss. So this is actually what I've said. This is a traditional source of counterfeiting. And that's something we can see. That's how things are actually getting done. And these are the electronic chips that actually enter the supply chain and eventually in the systems that we actually buy. So there are quite a few different scenarios, but that's something I will avoid discussing. That is, how do we contaminate the supply chain that we actually try to trust? And that particular discussion, I will not have it today, but we actually can pinpoint global, or what I call areas, where we believe that such supply chain contamination is taking place. But that particular data, we don't have it for United States, we have it for Europe. Why is it important? Definitely, in the United States, it has the implications both in consumer electronics and also in defense. But when it comes to consumer applications, we actually see it, that impacts global electronics. And so that actually brings us to that, is it possible for us to use methods or mechanisms that will allow us to detect all of these counterfeit electronics? So counterfeit types, there are quite a few, and I will not go into that much of a detail. But the whole idea was they are either recycled, they are remarked, or they are overproduced. But now, as we will actually learn, that there is another issue, and that particular issue is actually cloned integrated circuits or cloned electronics. And they are exactly the same, they are brand new, but there's a likelihood, or there's a possibility, that particular design actually has been tainted, or there are certain Trojans that are actually sitting inside that particular design. You have to understand that most of the time, traditional MOSFETs, power dissipation is about 1 femtojoule per device. That is something we cannot detect. If I have 2 transistors that are actually the Trojans, that will be something that will not be able to detect. Doesn't matter what means we apply. And they actually can corrupt and make the whole supply chain insecure. So these are what I call, for only for academic purposes, what are the different markings that we look for, and what are the different processes that we actually can use to identify all of these different counterfeits. So now question is, why is it important? Fun part was, this was actually about 14 different counterfeits, or what I call authentic and counterfeits, that were actually given to a few labs, academia and industry. And there were about 4 false positives. So in other words, we do not have the trust that the data that you're going to get or identification that you're going to make is actually correct. So that actually brings us to some signs. So these are very traditional integrated circuits. And so what we do is we just said, hey, the thing is, by the way, so if you would like to find out exactly what's happening, we actually can do quite a few imaging or different testings and so on and so forth. But if you like to look at it inside, one very good way is actually simply use it, take a look at it under X-ray. But X-ray happens to be a destructive mechanism, and we will never ever recover our chip again. So one way out is that's going to make Anisbhai very happy is the use of terahertz. So this is actually a method that we actually came up with at the University of Connecticut. And we actually make about what we call 5 spot measurements. And we actually try to extract the refractive indices. And so this is actually one of the systems. Unfortunately, this is not Anisbhai systems. This is another system that is made by Meldo. So what we do is we actually look at what we call the time domain data. And that actually shows that, hey, the thing is, there are certain reflections. This is from the top surface. And then it is actually interacting with actually exactly where the chip actually sits inside the die. Nothing interesting yet. Then we said, okay, if we subtract one from the other, front minus the back, again, it doesn't say that much. So there's nothing that we actually can say or utilize that will say if it is a counterfeit or not. So at this particular time, we were actually given 5 chips from Honeywell, and they did not tell us if they were counterfeits or not. So we actually went to the refractive indices. And so this is, again, the refractive index. And again, it doesn't tell us that much. The idea was that if the chips are sitting at the center more or less, and we actually subtract the front from the bottom, then there's a likelihood for good chips, that particular answer should be 0. And that's exactly what we see in this particular green one. So on the other 2, they are either they were actually polished, that is the 2 surfaces on the either sides, the top and the bottom, there is a dimensional difference. And at the same time, there's a possibility during polishing to get rid of those markings, there were certain elements that were actually used that is also going to have a signature in my terahertz. So we actually concluded that the green one happens to be authentic and the others are actually counterfeit electronic chips. And that was exactly the case. But the beauty is that this one does not require us to compare these results with any standard, or we call a golden chip, to identify the counterfeit. It doesn't require us to apply any bias, so we're not powering it up. We are not comparing with anything else, so it's a standalone detection mechanism. So this is, so what we see that, hey, the thing is, terahertz actually has the potential to detect standard, what we call counterfeits. But now the question is going to be, is it possible for us to, and so these are what you call certain things that if they're sanded, we know exactly what the signature is supposed to be. If it's contaminated, we know exactly what the signatures are supposed to be. And later, we actually compared all of this data with XRD to identify if there are certain contaminants. And in one case, the fun part was we identified antimony. Antimony is something that we do not use in electronics. So we actually found out that there's one sander that uses antimony, and we can actually find out exactly where these sanders are. Or in other words, we can do forensics, and we can tell in which country and where this particular counterfeiting technique is actually getting getting done. Now, we'd like to see, is it possible for us to see using terahertz? Terahertz has a longer wavelength, so it does not give us that much details. X-ray does, but X-ray destroys, terahertz doesn't, because it's the non-ionizing radiation. So on the left, we see the black and white is an X-ray, what we call image, and the colored ones are actually the terahertz images, and it does not give us that much details. But we have something different. We can enhance these images by using some very simple maths. And once we do that, this is what we actually get. And if we do it even more, we actually can say that exactly what the dimensions are. And then we actually can compare that with the X-ray image, and we actually have an enhanced terahertz that looks like X-ray, but not as great as an X-ray yet. So these are some of the results that we actually have. We can discuss it later if you have any questions, but I will actually move on. Now, so improvement is way better than what we actually have using what we call standard terahertz imaging that we actually can employ. But now the question is yes, there's a possibility we can detect, but can we deter? And this is where people actually have come up with physically unclonable functions. We have DNA signatures that actually, these signatures are employed to make sure that we are dealing with only authentic integrated circuits. But DNA, there's an issue because of what you call, over time, the degradation, at the same time, the possibility that it would actually be replicated by someone else. So the question is there something else that we actually can do that is going to make these signatures unique? I will move on. Okay, so we actually came up with something called engineered nanostructures. And these are simple geometric structures that we either draw on the what you call packaged IC, integrated circuit, or some other location that the manufacturer can decide. And these are very easy to draw. So we can either use impression to actually come up with a design like this. And the dimensions, it doesn't matter. It can be big, it can be small. But the fun part is these dimensions are rather unique because they are known as metamaterials. Okay, so first thing. So what we did is somehow we actually had on the surface of a chip, bonded chip, we actually have designed something. And then what we did is we actually had a laser pointer, which is a very standard laser pointer as an example, something like this that we use in our classrooms. And that was actually directed onto the surface of the integrated circuit. So we actually can move it around and look at the reflection. So the reflection is this is a standard reflection of the laser pointer. But whenever the laser pointer hits that particular tailored surface, it gives rise to another reflection. And that is due to this, we call negative refractive index. Because if you go back to high school, if you remember that we say that Snell's law of refraction, that is the incident light and the transmitted, they're on the other side of the perpendicular, but in a metamaterial, it happens to be on the same side in the third quadrant. The refractive index happens to be negative. So this is the sign that whenever we see this, we know that there is a structure, or in other words, it is the first tier of investigation saying that that particular structure has been detected. So there is a likelihood it is authentic. But then you'll say that maybe someone else did it. And that's a possibility. So what we do is that red picture that you see is actually taken from my iPhone. And we actually analyze it, which is a very standard YIQ image analysis. And this is a reconstructed image. We can reconstruct it. But important part is, so this is something we can store and we can compare. Question is, are there any embedded message inside this? Answer is no, there isn't any. But we can. We can embed codes. So this is actually a pattern that we wrote. So 5 means 5 micron by 5 micron, that's a 0, 0. 0, 1 means 10 micron by 10 micron. And we can make it, so this is a 32-bit embedded code. And that embedded code represents a certain geometrical pattern that is distributed and written on that particular die. So this is the reflection that we get, the image that we analyze. And then we actually can extract all of these dimensions by simply looking at the reconstructed image. Or in other words, we actually can embed the code and we can recover the code. And that is going to tell us if this is authentic or not. If it's a counterfeit, they can copy one, but they cannot copy all. So, but again, that actually is something that we utilize now. That is, we have to record it and then we need to compare it later. So this is the fun part that we actually had with the degree of difficulty and this and that and so on. Question is going to be, how do we play with it? When our other question is going to be, how fast can we do it in the production line? So these are the things that we actually need to take a look at. And we can simply look at that if I print it up then how fast can we get it done? Now, other question is, why do things so difficult? This is actually what we call a growth disperse inspect process. And this is as good as anything can be. And this is done by simply what we call, we actually grow what we call zinc oxide nanowires. This method is not only for zinc, it can be for any nanostructures. And we do it hydrothermally because it is actually something that becomes way cheaper. And then we put it in a solvent, and we use a simple droplet to put it on the surface of the what we call integrated circuit. And then it looks something like this on the right. And the fun part is that each and every droplet happens to be statistically unique. Or in other words, I can give the whole recipe to our counterfeiters. They will do exactly the same thing, but their signature is going to be different from the signature that we had. So if I simply take a picture of this particular signature and I copy it later, then I will know exactly if it is a counterfeit or not. And this particular process is fast because if it is a production line, and it can be done on multiple levels, on the box, on the integrated circuit itself, and so on and so forth. And we do the same thing. We look at the imaging and so on and so forth, and we can extract all the data later, and we actually can compare. So yes, they are very unique. And this is a mathematical analysis saying that these are all very unique signatures, all came from the same process, but the two different droplets are totally different. Now, secure electronics. So I will finish it at this point. Because that is another hour-long discussion. These are simples, but now the question is going to be, how do we detect clones? And that is going to be a challenge. And the detection of clones, there have been different suggestions and so on, using noise at the level, at the floor level, and this and that, and so on and so forth. But these are all suggestions. Nothing has been implemented yet. And the worst part is going to be, if I have a clone that already has a Trojan inside my design, then it's going to be practically impossible for us to detect if we don't do something different. So we actually had a few ideas. Some of the ideas actually we have discussed with Dr. Rahman. We'll discuss it at a proper time later. But there are also what they call design, but there are also suggestions that are made using changing or adding circuit elements during that particular design. And that actually is something we can discuss at a later time as well. But does it matter? Do we have to do all of these things? And this is something that Dr. Mizan Rahman actually suggested, and he touched on it. Yes, it is important. In a cyber-connected world that will champion for IR, trusted electronics is a must for connected systems and global security at all levels. If we don't do that, then connected systems means from traffic control to banking. These are all connected systems. And any electronics that cannot be trusted is going to be a disaster. So with this, I'll end my talk. But, oh, by the way, so these are some of the things that we actually had done with something that we came up with called memristors. These are physically unclonable functions to actually deter people from copying or for safeguard safety of electronics. So these are 1-bit memristor puff. And these are how we actually make memristors, which is actually fun, using nanostructures and so on. And this is something that we actually can make it compatible with VLSI, because we actually can make these memristors using hafnium oxide, and that is your gate layer. And that actually doesn't require that much actually change in the manufacturing process. Something compressive sensor is going to be an example, but end of the day, we can do whatever we want. We're only limited by our imagination. Thank you so much.
Thank you, Mehdi. Thank you. Very in-depth and impressive presentation again. So I'm sure there will be some questions for Dr. Anwar at the end. So thanks again for your great presentation. So let's move on to our last but not the least, the last speaker, Dr. Anis Rahman. Let me introduce him with some little bit intro about him. Dr. Anis Rahman is an acclaimed scientist in the field of semiconductor and nanotechnology. He's a winner of many scientific awards, including NASA Nanotech Briefs, Nano 50 Award, and Nano 50, that's the name of the award. He won that twice. CLEO Laser Focus World's Innovation Award 2015, MP Corrosion Innovation of the Year by NACE. Dr. Anis Rahman is the founder of Applied Research in Photonics, which is known as ARP, a leading Terahertz company located in Harrisburg, Pennsylvania, serving semiconductor and nanotechnology industry. Among others, he invented the dendrimer dipole excitation, a new mechanism for high power continuous wave T-ray generation. With this T-ray, ARP has created a number of new scientific instruments, including a camera-less lattice resolution 3D imaging technology that can see and analyze defects below the surface of semiconductors and nano materials. And also Terahertz time domain spectrometer is something that he also worked on. He has delivered many keynote talks and invited seminars on semiconductors, nanotechnology applications, etc. Anis is a recognized scientific leader and a member of scientific organization, including the American Chemical Society and the Optical Society of America. He is the past chair of the Optical Metrology Technical Group of the OSA, past chair of Small Chemical Business Division, and past chair of the local chapter of the ACS. Anis also received awards from the Omics International Keynote Recognition Center for Dermal Research, Rutgers University, the Entrepreneurial Leadership Award by the Henrietta College of Pennsylvania, and the Harrisburg University of Science and Technology. So let's welcome Dr. Anis Rahman. And I couldn't resist saying one little thing about him. Anis Bhai and I go a long, long back. Jokhon Anis Bhai was doing his PhD in Wisconsin, I was actually doing my undergrad in Wisconsin in my engineering field. So thank you, Anis Bhai. Please, begin your presentation.
Thank you, Faysal. আমাদের beloved Ronnie. অনেকেই হয়তো জানে না. So as you said, we go back way back. So anyway, let me share my screen and my presentation. So share. So can you see my screen now?
Yes, we can.
Okay, wonderful.
Yeah.
So thank you again for this wonderful session. We actually have learned a lot from Enayetur Bhai, Dr. Mizan Bhai, as well as Mehdi Anwar, Professor Anwar. It's really exhilarating experience, and semiconductor is at the heart of whatever we do today. So today I would like to say a few words on T-ray, which is terahertz. Mehdi has spoken a lot about it. T-ray, camera-less metrology of semiconductors. So the plan is why T-ray is, why camera-less imaging necessary, and then go through some of the intricacies of the camera-less imaging at lattice resolution, and finally a few examples. This apparently it had time, so I'll change that. And I will skip some of the slides so that we can go to the Q&A sooner. So the current state of the art are not adequate for characterization at the nanoscale or lattice scale, which is 1 nanometer is 10 angstrom. So lattice scale is the angstrom scale, which is smaller than nanometer. Semiconductors, interfaces, nanomaterials, which comes from 0D, 0 dimension to 3 dimension nanomaterials, and nanomaterial interactions. All of this requires certain characterization and measurement that current technology or state of the art are not adequate a lot of times. So as the old saying goes, if you cannot measure it, you cannot manage it or control it. So measurement is the key no matter what we do. Driving car to making 2 nanometer node semiconductor transistors, as Dr. Mizan explained and Enayetur explained. So the challenge is the sub-angstrom resolution imaging without electron microscope or an AFM or an STM, etc. That means we have to overcome the AABEA diffraction limit and then solve the problems of imaging with bigger wavelength. So here is one slide for our company. We started back in 2003 doing lots of government research work. And then we had our first dendrimer waveguide patent awarded in 2006. So slowly we came forward, and then we survived by offering services, contract research, and selling a system or two here and there. That's how our company progressed. And then in 2016, we were able to achieve less than 1 nanometer resolution, which was a big deal at that time. And then 2018, we demonstrated the lattice imaging with bigger wavelength. So here are some of our collaborators, and many of them are our actually customers, including Samsung Korea, Samsung Japan, ON Semiconductor, Los Alamos National Laboratory, Lam Research, Penn State University, Anthropocene Institute, Procter & Gamble, they also have application, TSMC through IMEC, Kyoto University in Japan, Army Research Laboratory, General Motors, Coppin State University in Baltimore, SUNY at Stony Brook, Leidos Biomedical, also in Maryland, Rutgers University, University of Arkansas, Université de Savoie in France, and University of Duisburg, Essen in Germany. But there are many more that I haven't mentioned yet. But so, what is the big deal? The big deal is, as far as imaging is concerned, it has certain physical limitations. In 1873, Ernest Abbe established that when you are using a microscope or some other kind of imaging instrument, the smallest object you can see without any diffraction or aberration is half the wavelength of the light that one is using for imaging. So that has been the Bible all the way, even today when we use wavelength for imaging. Electron microscope can see lattice image because it has the wavelength of 2.5 picometer at 200 kilo electron volt. So therefore, it can see the lattice image. But not everybody can afford an electron microscope, and one has to be an expert. And over the decades, scientists and engineers have always been trying to overcome this limitation. Why can we not make lattice image with bigger wavelength? So we happen to be one of the team that have been able to solve this problem. But at the upfront, let me mention that this overcoming the AABEA diffraction limit is necessary, but it is not sufficient to get to the lattice resolution, because roughly from 9 micron to 3 millimeter is the range for terahertz or T-ray wavelengths. So even less than half of 9 micrometer resolution is achieved by lens system. It is nowhere close to lattice resolution, which is on the scale of angstroms. So what needs to be done? it need to be overcome. And the stratagem that we have worked out is we use a thing called Beer-Lambert's law. In all imaging is mostly all camera system is done in a reflection. So the Beer-Lambert's law we rewrite in terms of the reflectance. Also, but our instrument can do it in transmission as well. So I'll come to that later. And then we digitize an object in 3 dimensions with our nanoscanner, and then use the computer algorithm to generate the image. So before going to the details, let me say a few words about terahertz, as so eloquently introduced by Mehdi, Professor Anwar. T-ray or terahertz radiation used to be called the terahertz gap a few years ago, simply because there was no man-made terahertz source. So back in the mid-80s, Austin made a photo switch which could generate the T-ray. He achieved about 1 terahertz or so. So the power is always an issue, because most of the photo switch in vogue today generates only microwatts of power. And so this power, because if we use materials that absorb a little bit of power, then a transmission or even in reflection, not significant power is coming to the detector. So there are more than one ways of generating this terahertz. So one technique that we came up with called dendrimer dipole excitation, or it's a polymeric material that we use to, this cartoon over here, as you can see, this is a dendrimer molecule on the left, lower left. And so we dope it with a chromophore to create the charge centers, which are what we call is the dipole. And those dipole are excited by a pump laser, and then it radiates at the T-ray. So it's almost like a laser system, except not a 3-level laser, but it's a multi-level system. And on the right, you see a picture of Donald Tamalia, who is my collaborator, also my mentor. And he is the one who first synthesized this dendrimer molecule, which is really tricky. And then we took that dendrimer molecule, we did a lot of fundamental studies on it as my postdoc years, in my postdoc years. And then we found this way of generating terahertz out of this, which Don Tamalia has lovingly named as a Rahman-Tamalia effect. So here's the dendrimer molecule, and I'm not going to go through all of this. The key here is that this dipole density, N, which is directly related to the secondary susceptibility of the material, and unless that controls the conversion efficiency of pump laser into the T-ray. And so we have a control on that by means of doping and using different generation of dendrimers. And then, as you can see, this dendrimer dipole moment becomes a function of position. It's no longer fixed, just like the inorganics. So that's an advantage. Here's the basic mechanism, how we generate the T-ray. With that, this is how our system looked like on the upper left. The laboratory prototype back in 2016 was here. We had a live demo at the university with the students and postdocs, etc. This is how we mount the sample. Here is a wafer that's mounted on the scanner. And this is a small sample arrangement. For bigger sample, like 8-inch and bigger wafers, the wafer is mounted and it does not move. So we have an optical circuit which is energized by an optical fiber which delivers the T-ray. So that scanner moves, but the wafer remains stationary. So this is for preventing the vibrations. Bigger wafers are very prone to vibration. So 8-inch or bigger wafers can be mounted either vertically or as well as flat horizontally on the ground or the optical table or sample mount. So with that, this is the scanning. Once the scanning is done, then we go to the imaging. So the basic difference with a camera or CCD system is that you must have a focusing lens that will focus on the focal plane array. The focal plane array then spits out the signals or electric signals, a voltage. Then in your camera, you have an ASIC or application specific IC, which converts that signal into image and writes in a file. So we're doing basically same principle, except that we eliminated the focusing lens and the CCD by a nanoscanner. And then again, utilizing the Beer-Lambert's law, we generate the BLR matrix or Beer-Lambert reflection matrix. And then that 3D matrix is processed and imaged by the computer. There is one of the algorithms that we borrowed from NASA. This is published in 1986 and 1982. These are the two seminal paper that outlines that algorithm. And the key here is that if we scan the same thing over and over again, then we should get the same profile. And the other thing is that as you change the material, the reflection changes. So that is the contrast generating factor. And then those contrasts or intensities are utilized for generating the images. So there are cameraless system has some pros and cons. In the cons, it needs a scanner or a nanoscanner. It's not in real time. So that's why it's good for only scientific imaging. And lattice resolution scanning takes longer, normally overnight. And it doesn't have any elemental analysis. The spectroscopy part doesn't have any elemental analysis like the SEM has. So, and not handheld yet. So this is a tabletop system. On the other hand, the good things is that you don't need camera. It's not dependent on the CCD. Resolution is chosen by the user. It can do 3D imaging and so on and so forth. So, you know, I don't want to overshadow what Mizan Bhai and Enayetur Bhai have already mentioned, but the single wafer goes through a tremendous value increase. You know, $100 wafer can become more than $1 million wafer, depending on how many chips are being built on it. So it takes a long time to develop the process. So our instrument is you know, aimed at shortening and making it easier and accurate. So with that, let me show you a little bit about the semiconductor interfaces. And Faysal, you can warn me of time if I'm taking too long.
No, you're good. You're good. Thank you.
Okay, wonderful. So then semiconductor interface is key in semiconductor manufacturing, because once you have a silicon wafer or substrate, on top of that, we have to add layers. So layering, patterning, and that layer can be semiconductor, that layer can be metal, that layer can be something else, photoresist or all other things. So that's why the interface is the key for successful semiconductor manufacturing. And there are more than one kind of interface. Interface simply means that when one material is deposited on another material, the joint of the two material is the interface. So there can be misfit lattice type interface, there can be identical lattice interface, there can be rough surface interface, diffusion type interface, as well as mismatched compound semiconductor hetero interface. So as you can see, the problem is that this is a thick, you know, on wafer, you have layer, etc. So without breaking it, how do we see below that if the interface is good or bad, or is process need to be adjusted so that this interface is you know, perfect the way it should be? Because if the interface has delamination or contamination or inclusion or that kind of defects, it will not function properly. So before I go to the interfaces, here is also another problem is that the whole wafer imaging is not possible by the current technique. Any of the current technique can see a spot, but what about seeing the whole wafer? Because when the patterns are done, die are made or chips are made on a wafer. You know, each of this rectangle you see here or square see here is a single chip. So those are cut into separate pieces, what they call a singularization. And then they are connectorized, then they are packaged, then they are tested. But if the wafer on the upper right side, if you can see, the wafer has defective area, and we could see that ahead of time of singularization and all the connectorization and testing, that saves not only money but also time. So that's why it's also important for whole wafer imaging as well as the interface analysis. But there are many other applications. I may come a little bit later if time permits. But what we do is three-dimensional imaging, meaning that it's not just the surface texture, it is actually the volume image. And then we can see it layer by layer. These are not different layers. These are the lattice on this image. These are the lines that we are seeing. Those are the actual lattice spacing. But layers are this one. Here you see on the left, I have 3 different layers. On the right, another 3 different layer on the on the YZ axis. And we can have as many number of layers as possible for the ease of inspection. I am skipping this one. So here is another example of silicon carbide wafer. So on the left, as you can see, the image is very monotonic. But when you see under terahertz or T-ray, you see a lot more details that cannot be seen by optics. And also we can see the lattice image here on the upper right. We can calculate the lattice spacing, lattice constants, and determine the polytypes and so on and so forth. Here is a line, what is called as a dislocation line, and the nanograin boundaries are visible. We can measure the thicknesses of the epitaxial semiconductor layers. We can now see when you see the very close 1 micron by 1 micron by 1 micron volume, we can see different layers of the interfaces, how they are deposited. And then we can characterize those interfaces. On the middle, you have this layer 1, layer 2, layer 3, layer 4, and layer 5. And between each of those layers, we have different interfaces. On the upper right, you have this is a line that you can see between 2 different almost identical lattice, but the interface line is visible. So this is a very good interface on the upper right. On the left, on the middle, the interfaces are characterized as the layer 1 is the misfit between layer 1 and layer 2 misfit lattice interface, and so on and so forth. So also we can measure the nanograin size. We can image them and measure them. These are 100 nanometer by 100 nanometer images from which we can measure the grain size. And if we had nanoporous sample, we can also quantify them. So this is all about measurement. Here is the last image probably. Carbon was deposited on something, and there's missing material on top that we can see and we can measure. This is how the measurement is done. So let me skip this portion, which is a nanoscale interaction. Here we characterize the quantum dot interacted with the ionic polymer liquid. So, this measurement, this has been published by Los Alamos National Laboratory scientists. On the upper left is the sample as synthesized, and the upper right after swelling in DI water for overnight. So those are the characterizations were done for them. More of the same, and let me go to the conclusion that AABEA diffraction limit has been overcome by T-ray multispectral imaging as implemented here. Achieved sub-nanometer and sub-angstrom image resolution with T-ray in the X, Y, and Z directions. Combination of a smart nanoscanning spectrometer and algorithm replaces a CCD for sub-nanometer resolution. It is non-destructive, non-contact. It can see subsurface and layer by layer analysis. It can inspect 0D to 3D materials, lattice defects, stacking faults, all kind of defects, non-uniformity, inclusion phases, etc. So this is applicable to any semiconductor industry, nanotechnology industry, be it in Bangladesh, be it in anywhere else or in the US. So with that, I thank you for your attention.
Thank you very much, Anis Bhai, Dr. Anis Rahman. Yet another very impressive and in-depth presentation. Again, thanks to all our panelists, Mr. Enayetur Rahman, Dr. Mizan Rahman, Dr. Mehdi Anwar, and Dr. Anis Rahman. So let's open up the floor with some questions. So please feel free if you have any questions. And I have a question, but I'll hold on until you guys raise any questions, please.
So looks like, if I may ask a question to Enayetur Bhai and Mizan Bhai, whoever wishes to answer. How soon you can predict that Bangladesh actually may have some fab of their own, even if not the IC fab, maybe PCB, small scale and large scale?
PCB fab is easier to do compared to IC fab. Even India could not do the fabrication. I think the difficult part is infrastructure and very pure water. Even Taiwan is suffering of the pure water supply and everything. So India took 2 attempts. India could not go into fabrication. But PCB is, of course, possible. PCB fabrication, I think in Bangladesh, most likely Walton is trying to do PCB fabrication. So that is possible. I don't know, Mizan Bhai, you want to add anything to it?
Only thing on this why I can add, doing the fab is good, but keeping it busy is the challenge.
Right.
So it's a capital investment. That's part of the story. If you cannot keep the fab busy, you're going to lose your shirt. On the PCB side, I just made 49 PCB with Walton. I got the board yesterday. So we're trying to figure out why we go China when I can do it with Walton. So Walton has a good fab. It looks reasonable. By the way, it is not heavy layer count boards. So it has started. So going back to your interest in fab, and we are all interested, but where the big money is going to come, even if you make it, is my question we have to set back, is that a $1 billion or several $1 billion India wants to invest, our $1 billion or 2 or 10, is it worth spending in the fab or the building the other ecosystem? Then you kick in the fab when it is the right time. There isn't any, remember, in '87 when Maurice Cheng did it, it's not that capacity, that process node, easy to build, easy to produce. But I would say this, there are my friends in the Silicon Valley, they own their own fab. Right. These are for specific focus ICs that they build. That their own IP, like again, is the space where there are some of my friends have their own fab because yield is not there and they cannot get it in a general site. So if you get a niche fab, those make sense to me. A low investment, customer is there, and a real use of it there. But mass scale, high volume, I don't want to comment on it. This is a very controversial topic.
Right. Well, related question, if I may ask, just as a follow-up. So on the PCB side, if there is a business plan for, let's say, millions of volumes of PCB that need to be processed, is it possible to contemplate that kind of opportunity in Bangladesh, and will there be investor or industry interested to engage?
Absolutely, yes. So there is no reason, if China can produce, Anwar Bhai Jita mentioned as a counterfeiting. It is killing the industry. Thanks for reminding Anwar Bhai. I am using chips, which there is no imprint on it. In fact, so I could not buy chips without, I have to buy chips without the label on it. Then I opened up a few boxes, which are Fortune 500 company. I opened there, so I want to find out what they do. I found the without marking chip in their system. So these China, there's all going for them. We should be staying away the way China doing business. And China's business gonna lose sooner or later. Smart people like you guys gonna say, look, automatically detect and deter and kick them out. Now, that's where the vacuum is created. So my request would be PCB fed in a large volume is right and ready. And we should not look for Bangladesh volume. We should look at the India volume and Asian volume to hit the price range people are looking for.
Mm-hmm. Anyone else?
Enayetur,
Yeah.
one slide that you need to add to your history. National Semiconductors, 1959.
Mhm.
They started it in Danbury, Connecticut, before they moved to Silicon Valley.
Okay, sure.
And by the way, that infrastructure is still here. You can come and look at it.
Wow.
I
And that's
would love to. I would love to come and do that.
That's interesting.
Anwar, actually, it's a very important thing you mentioned about this counterfeit thing. I actually extensively visited many countries, including one big Asian country. You know which country is. I saw people are doing reverse engineering. I saw, so in consumers area, I think it would be, looks like almost impossible to stop because, you know, a lot of toys and all the stuff, but anything infrastructure related, you know, like say financial institution, any other things that is very sensitive in nature, I think it is very, very important that all chips are, make sure there's no counterfeit is getting into it, and that will be a disaster.
the thing is, at present, Battelle actually has a system that, I mean, but these are for traditional counterfeits. So from measurements, they actually can say there's a likelihood there's a counterfeit versus authentic. But the challenge is the clone. Because when we open up the clones, the few that I have seen, they actually change it at the design stage. But the fun part is either there are some misspellings or they actually have what you call the different modules, they have moved them around. So if you compare them with the authentic one, that is actually a key saying this is actually a clone versus the other one. But it is practically impossible for you to decapsulize each and every design just to find out if something is there or not. And the worst part is,
a lot of companies, sorry, go ahead.
But I don't know if they've added 2 or 3 transistors or not, because if you remember, what do you call, it was Syria. Israel turned off Syrian air defense before they bombed it. And that was in Spectrum, IEEE. And that was 10 or 15 years back, or even more. Now think about now where things are.
Yeah.
And that is actually a challenge because over here, US Navy, they got a shipment of counterfeit Xilinx chip. And then they actually were sued. I mean, they actually found out that the guy's actually importing it and he's sitting in Boston, in somewhere in Massachusetts, and so on and so forth. So this is going to be, I think, design phase, as you said, Mizan Bhai, that testing, design, this is where Bangladesh definitely can contribute. But if you ask me that, hey, do I set up a fab facility? My answer is going to be, hey, do we have the return on investment? And that is not exactly likely at this particular time. Maybe we should spend our money doing something slightly different.
That's right.
But testing, design, oh, definitely we should go for it. PCB, definitely.
Yeah. Testing, if I may just add, the testing is universal. Everybody needs that. But going back to the counterfeit, it's a no-brainer. We don't want counterfeit currency. So why do we want counterfeit IC? This is the
Question
same.
is nobody wants it, but this is embedded in such a way it can hurt the whole thing. You know, that's the problem. It's not only counterfeit they're making money. It's also counterfeit they can damage. You know, like you know, Anwar was mentioning about the Syria and Israel and everything. It is so easy to get into all those things. These days, also the GDS2 level things are stolen. and they fabricate it. That's exactly the same, because very easy to make the electronic copy of the GDS2, which actually goes into the fab. But I think companies are also looking into those GDS2 and see who did that. It doesn't even require reverse engineering. Basically, you go and plug it in and stuff like that.
Exactly.
So there is a way to track those also. That's one reason when we do business in Bangladesh, we are going through, man, Mizan Bhai knows what the hell we are going through. I mean, difficulties with all those cage model. In fact, our engineers are not even allowed to go into the room with their mobile phone. That's the software industry has no clue. They have to keep their mobile phone outside, their body search, and they have to go inside. It is monitored through the video camera and everything. And it is so, we call it cage model. Even Dhaka we're doing when we're working on such an advanced node and stuff like that. So there are a lot of requirements we have to do this semiconductor design in Bangladesh.
See, the thing is, one aspect is counterfeit economically impacting countries. That's fine. I mean, not fine. I mean, that is there. But the worst part is if counterfeits, if Trojans actually enter what we call this cyber network, and that allows us to infiltrate banking, commerce, education, healthcare, you name it.
Yeah,
exactly.
And that is a disaster waiting to happen.
Mm-hmm. So can I ask you a related question to any of the panelists? So I do a lot of cybersecurity work for the federal government. So it's on the network side, it's on the application and the system side. But on the chip level, like in the ICs, if there is any kind of security vulnerabilities that's embedded there, my knowledge is very shallow there. I mean, like what kind of vulnerabilities we may have and what can we do to quickly rectify that? One of the speakers was saying that it's extremely difficult once the chip is designed and embedded, then if there's any kind of issue, it's extremely. So is there any work or is there any kind of way to avoid those vulnerabilities into the ICs in our systems?
I think one way is the testing that Dr. Anwar has developed. On the genuine, in fact, I know another company, they have developed a DNA signature, and that has been legislated in the DoD Missile Defense Control, cannot have a chip unless they match the signature. So the signature is also Dr. Anwar's signature. Those are the kind of approach that we need to take, I think.
Say, as an example, US government has, they have adopted the DNA signature, but the DNA differs with time. And it is also a likelihood it can actually be replicated. So it is not good, it's going to be a problem later. But the challenge is the traditional, what you call counterfeits, that we actually can come up with our different testing metrics and so on, that will be, maybe hopefully we'll be able to identify. But if there are if there are what you call hardware, we call Trojans,
right?
If they are actually in the design phase, then it's going to be practically, as I was saying, that one gate, I'm not talking about the 3 nanometer, it's going to be even worse. It actually dissipates 1 femtojoule. We can't measure 1 femtojoule. There are no infrared signatures. So if there are 2 or 3 transistors, that is going to change the whole dynamics and will not be able to detect them. And so far, there are lots of studies saying that below the noise floor analysis and this and that and so on, but nothing has been proved yet that is going to work. So that is going to be a challenge because we don't have any way out. And we don't know if there are already Trojans actually already sitting, waiting to be activated. We don't know.
Yeah. No, thank you.
So Faysal, I think just add to it, anything on the cybersecurity, all the hardware supply chain has to be managed.
Exactly.
Where it is coming from, who's building, and that's why every country wants to build their own chip. This is one reason, because the chip is coming from somebody else. You have no idea what is there.
Exactly.
And that's why if Bangladesh, I think they have mentioned it, if they can get into blockchains, that is actually one security paradigm that actually is actually going to be enforced. I mean, it's a law when it comes to pharmaceutical goods, but not for anything else yet, that it must be traceable starting from the origin.
Mhm.
So we actually need to have something like, starting from when I start collecting silicon, it needs to be actually have that
Right.
blockchain signature. So actually
Sure,
I can trace it back if need be.
Yep. So there's a physical security aspect of it as
Oh
well.
yes, oh yes.
Yeah, yeah. Okay. Thank you. Thank you.
But Enayetur bhai, this guy, I think Walton's CEO is with this technology roadshow.
Oh, is it? Yeah, yeah. So I met him also, I think in Bangladesh, yes. Oh,
And
so he's coming.
as the senior, no, not senior secretary, he's the, what do you call, one is a cabinet secretary, and the principal secretary is also here, along with Salman F. Rahman.
Yes.
Yeah, yeah, yeah.
Yeah. Mhm. Okay, so we have a couple minutes for any other questions.
Well, it seems crowd has
Okay,
been
great.
shrinking quite a bit.
Mm.
Probably, I don't know if you'll disclose it, but Enayetur bhai or Mizan bhai, what is your split between the US customer base versus the overseas?
Our 100% customer is from USA right now.
So you are heavily dependent on the US business.
Completely 100% US customer right now.
Mhm.
Yeah, that's what my understanding is, but I believe there is a huge potential in Bangladesh because it
Yeah.
is
So
not
what is-
even looked into at this point.
Right. So what is happening right now in semiconductor space looks like there'll be China camp and then US and the rest of the camp, USA and other things. So, there's a big potential in China. Also, China's government is spending billions of dollars, $100 to $200 billion. They're developing a fab in Shenzhen because TSMC access will not be there anymore. So there will be competition. Okay. So interesting enough, I found that even Taiwanese company, they do a lot of work, like Mizan earlier mentioned that, all those growth of China because of Taiwan, and the US government is now trying to stop it. They say, wait a minute, you are taking full advantage of all of our technology and everything, and now you're going to compete with us. So US government is trying their best to stop all those things. So what China knows that this is coming. Mizan Bhai actually visited Shenzhen and we talked to some people there. So what is happening right now, there will be two camps. Even Taiwan is some company, they literally split their company. One will work directly with China because China has huge business potential. Why lose that one? And also work with the US camp and everything. I think Bangladesh also can explore that because we have a good relation with China. We have a lot of business with China, but when we do with the US camp, we can split it. So, but actually there's a lot of opportunity, but for our case, we are actually went to Shenzhen. We are almost going to open an office, which I mentioned a lot of places. Mizan Bhai and I looked at the office in Shenzhen. We also we had a very, very productive between Huawei and all those things. Then when all those things started and pandemic started, we say, forget it right now for now, because we don't want to be a bad guy in front of US government because we're doing a lot of sensitive work here. So we stopped doing that. But what I'm saying is there will be a lot of potential in future.
That's precisely, I think, if I misstated my question, the business that you're building is to do IP and services for US clients. But if you think about the demand in Bangladesh, all the chips are coming from China, basically, even voting machines or even IoT devices, all of them just we are importing and then kind of customizing. So your business is founded on a resource from Bangladesh service, but then this is the other area. The demand in Bangladesh is going to be less reliant on Chinese chips. And in near future, I would believe that somebody would trigger that, hey, we have the resources, we can build our chips. It's a matter of building a fab. I believe Walton or some others might start looking into that, right? Have you looked into that?
Walton is not in the chip business, by the way.
But they are not. They are not yet. But I think the market should be there. There is no doubt there is a huge market and potential.
Maybe Mizan Bhai can address that question. We are exploring that. It's a good point. Maybe Mizan Bhai can.
Yeah, Sheikh Bhaiya, this is why we build Teton. So we build a separate company to focus on what you just said. Time is right. We gotta do it, and we cannot do it under the focus of Ulkasemi because we don't want to get defocused. So we focused on Teton. We'll talk about it sometime. Now, bigger question is, as I said, hardware chip design is 4 times expensive. Even Intel and foundries, they need $50 billion giveaway. They are profitable company, government giving $50 billion. That it is the rolling the ball. Bangladesh has all the people and 160 million people, like half of the American population. The market is all there. The question is how to roll it. And one thing I want to point out, in Dhaka, we have a BASIS, right? BASIS is an organization focusing on the software side. There is absolutely zero on the hardware side.
That is
I
true.
escalated it in ICT and other folks, even, okay, so I did escalate as far as I can go, but it is time that we get together and address the hardware foundation ecosystem. You know, asking Walton to get to a chip business would not be fair. They may have the money, they may not have the technology, people.
Right.
We need to work together, create the ecosystem. But time is now. If we don't get it, India, Vietnam, and others will do it, and it will not be easy for us to get in. Thank you.
On the cost side, like, you know, if to build a chip in Bangladesh versus China, are we cost advantaged?
Absolutely.
We are, right?
My number is, I can give you a 10 to 1 with United States.
Oh,
10
really?
to 1. From the resource, the problem in hardware is the IP cost, NRE cost, and the tools. They are fixed costs globally. That's why, even though resource and strength and technically we can fight, our 75% cost is burdening us. So if I have a chip that will generate profitable margin for me, then I can do my R&D. Until I get this 3 years bleeding time, what I do. This is the big question. As a company or individual, we cannot answer. We need a bigger authority come and help us.
That's why we need a Mahathir, somebody like Mahathir in Bangladesh, who has the vision, understand. Because, you know, to be perfectly honest, we can go and lobby the government. Then government will realize why in the world we are coming and trying to convince them. It should come from them.
Right.
And they say, okay, these are the, like Indian government is saying, anybody opening fab will give you $1 billion. They announced it.
Yeah.
What our government has to do, that Mizan Bhai said, that if you're developing a chip, say made in Bangladesh chip, government has to come forward, go through that bleeding time so that we come up with some success story.
But that's where I think government will never be innovative enough to come with the proposal. I think the technical mindsets who are the leader in the space have to present what the vision.
We need one Maurice Cheng, right? And one Mahathir. That's it.
I don't
We need to educate them.
Well, I might nominate some of you into that. Like, hey, you know, the thought leaders are in the US. All of you guys are very smart, and you have done it. So, I think reverse, trend of talent has been happening. Like in India, people have gone back. China, people have gone back and then build for their country. And Bangladesh, I think we are not that far when people will say, like, look, enough. We have done enough business in the US. Let's try to penetrate into our local economy, and that's huge. Bangladesh is a consumer-driven economy. Even if you build some small electronics, look at the mobile phone market; it's massive.
I think thank you everyone. Amra, we're a little beyond our time.
You had too many important talks on.
This is really good. I mean, today's session was amazing, and unfortunately the attendance was a little light, but the good news is we recorded it, and
are you sending it through the the mass list that we have, or how is it?
I think we should
we'll update it on YouTube, and you will get the link.
Yes, please do that.
As well as on the
website. Yeah, you can upload on the website. Should be.
Yeah, that too.
Right. Okay, so thank you again. Thank you so much for all the panelists.
We hope, just one word. We hope to listen to Mizan Bhai and Enayet Bhai again on
হ্যাঁ,
T-Con
আপনি
and
একটু
all
শেষ
other,
করে দেন প্লিজ।
all other things. And down the road, Professor Anwar and we may have some new results coming if we can get to our proposal. So, and the other thing is that I really do have a proposal for high volume PCB. And I would like to share that with Enayet Bhai and Mizan Bhai, if that's okay. So
Sure, we'll set up a meeting. No
yeah,
problem.
Absolutely, yeah, absolutely.
with that,
Thank you very much.
thank you all.
Thank you all. Thank you.
Thank you.
Have a good
Appreciate
one.
it. Thanks.
All right.
Goodbye.
Really
Assalamu
appreciate it.
alaikum.
Take care. Assalamu alaikum.